Good afternoon. We resume our talk here, and we are still at the initial stage of this series of lectures. The one that I'm going to be discussing right now will continue with some of the tools and techniques which are pretty common, and we'll just about reach the, we'll touch Six Sigma. We'll just make a beginning of Six Sigma as we go into this. You'd remember when we when we stopped the lecture in the previous session 2, we discussed how to take customer requirements and how to convert them into specification. That was something that we could do quite easily by asking people some questions and by asking our staff how are we going to be solving them. So we converted what is the customer, what is it that the customer wants, and how are you going to be satisfying that. Now the same process can continue as you go deeper into the process. For example, when I'm doing product planning, I would take direct requirements of the customers and I'll come up with design requirements. That is something I could do by going through this process of doing product planning. When I come to product design, I'll look at design requirements and I'll come back with specifications, parts and the item characteristics. When I'm doing process planning, which is the place where these parts are converted into the real process, into the real product. There of course we'll be doing again one other layer of QFD, and we'll be taking parts and input characteristics, item characteristics as the input, and putting through the process planning stage, we'll convert them into process operations, the specifications for the process. Once that is known to me, then I'll bring in process control logic and I'll try to come up with operations requirements. So starting with customer requirements, I come all the way down to what am I going to be doing on the floor. That's like, and at every phase I've used QFD. That's what I've done. Cost of mismanaging, of course, you know, we've already mentioned that there's going to be a lot of rework and returns for the customers, which is going to add up to failures and loss of profit and so on. That's something that we'd like to avoid. Commitment to quality is quite easy to detect. And if you look at these points here, problems are corrected very quickly with suppliers. Equipment faults are put right by improved maintenance people as quickly as possible. People are well trained. Partnerships are built with suppliers and also with customers. We understand both sides of the story. Continuous improvement is observable. If you go back to the same factory with some gap, a gap of like a month, you'll see some change there. And the surefire way of saying that something good is happening in the company is when business begins to grow. You get more orders. Some distinctions again. TQM, as I mentioned to you, it's not a program. It's a culture. It's a way of thinking. ISO 9000 is a set of guidelines basically to impact all quality related activities. These impact your practices and put your house in order. That is what is done in ISO 9000. Six Sigma is a technique-oriented approach. It's very heavy on techniques and results. And it's a business process. It's a process that impacts your business, that impacts your process and produces better results. Competitive positioning, how you want to compete. There are some tips giving here. Do you want to be the lowest price supplier? And do you want to target the market in a broad way, or do you want to go after a niche market? And do you do that by assessing your buyers, suppliers, competition and so on and so forth? These are a few different things that you must do right in the beginning. Then you determine how you are going to be adding value to this in this chain, how you are going to be doing it. If you just look at TQM, TQM also starts by identifying the needs and expectations of targeted potential customers, and TQM does help you in positioning your business, that it does. If you look at the elements of TQM, again there are many different elements and you can read them, you can see what they are. There are no real surprises there. This theme of continuous improvement, this is very important for the Japanese. They would do the same thing again and again, and every time they do it, they come up with a slight improvement. It's not like they're looking for a breakthrough, they're waiting for a breakthrough, which is the Western style. The Eastern style or the Japanese style is try to do some improvement every day. To the extent possible, make an impact on your process. And the philosophy of making each worker responsible for the quality of work, that's also very, very important. Let me give you the example of a couple of cases in which I was involved. There is an organization called BHEL. It's a very, very famous company, and the letters stand for Bharat Heavy Electricals Limited. What is their business? They produce power supply equipment. They produce the turbines, the steam turbines or the hydro turbines. They also produce the generators, and eventually they produce a total facility that can produce 250 megawatts of power or 500 megawatts of power. These are world scale generators of power. They are in this business. The example is as follows. I go around and I give talks on quality in various different places, and on one of those occasions I was invited to go to BHEL in a town called Hardwar. It's a very, very pretty place, and the Ganges, it's rushing down from the mountains and it's just reaching the plains, and water speed is very, very fast. And on the shores of this river there's this huge plant, the BHEL plant, where they fabricate all these different turbines and so on and so forth. Now, I was there to give a talk, and after some gap, I had some time, I had about an hour, and I wanted to walk around, and I asked people, could I go to the shop floor? Lo and behold, in a few minutes, I was in the shop floor. And they had these different machines, and all kinds of machining was going on, and different things were going on, welding and machining and grinding and so on. All that was taking place at these workstations. I found a gentleman. He was about 35, and I walk up to him and I look at him, and he kind of looks like he really knows what he's going on. He seemed to have good experience. And in his hand he had a turbine blade. He had a turbine blade in his hand, which had been forged by another system, and now he was doing the grinding on it. He was trying to make sure he gave it the shape, because it had to be aerodynamic and so on to make sure it functioned pretty well, and it was able to convert the steam's energy, the pressure, into rotation, and with that the shaft is going to rotate and so on. All that would happen if the blades were okay. And he was grinding these individual blades, he was machining them. Now that was something he was doing one blade after the other. So he'd take one blade, he would do the job, and then you'd do something, you'd make some measurements, you'd write something down, then you'd pick up the next blade, and you'd do the same thing, you'd do again some grinding and so on, then you'd make some very specific measurements, then take a look at it, make some corrections, and again you would make some measurements and so on. While he was doing that, he was writing down a lot of stuff. So I found him writing down, measurement A, B, C, D, and he was measuring these things. And there was a picture of the turbine blade, and the blade was somehow like this, and it would make these measurements at various spots, and it would write down some numbers there, 12, 14 or 12, and 8, and 6, and 2 there, and so on and so forth. He was doing this. As he was preparing these blades, he had that picture there and he was writing these things. And I kind of, a bit to tease him and a bit to find out really what was going on, he asked him, in Hindi we call such people Ustad. So I said, Ustad ji, what the hell are you doing? I didn't say hell, of course. I said, what in heaven are you doing? And he said, well, I'm making turbine blades. It's a very important part that goes into a huge turbine, and what we have to make sure is that the turbines are made properly. And that means the blades have to be made properly. So my job is to produce these blades. I said, well, I see that. I see you've got this diagram you make, and you're making these measurements, then you're writing certain things down, you're filling up some charts. It looks like he had some charts there, and he was doing this kind of stuff. He was doing that as the blades were coming out. And I said, sir, please tell me, why are you bothered about these, preparing the chart and so on and so forth? Your job is to basically fabricate that turbine blade. So basically, you'd be really worried about the turbine blade. Why is it that you're writing all these numbers down, making all these measurements? What is the use of all this? You're a machinist, you've got so many years of experience, probably 12, 14 years of experience. You should be focusing on machining. This seems like clerical work. Why are you doing this? This is the philosophy of making each worker responsible for what he is doing. And let me show you what happened. Let me tell you what happened. He gave me a very stern look. And then he asked me, sir, do you mind telling me who you are? I got a little somewhat shaken up. I said, well, you know, I'm a teacher and I've been brought here to give some talks and so on. And I had some time, so I came down to the floor and found you were doing some interesting things. So I wanted to chat with you a little bit. But I'm still very curious, you know, why are you bothered with all these, writing all these numbers down and plotting these charts? Why are you concerned with that? He said, sir, let me tell you something. If this turbine blade that I'm making, if the dimensions are not right at the right places, and suppose this turbine blade malfunctions in the big turbine where it is put in, there are like 50, 60 such blades, they will be put around a hub, and then the turbine, when the steam comes, it will start rotating. And suppose it is not balanced, suppose something is wrong with it, the turbine may basically fail, and that means the generator that is connected with it with a big shaft, it's also going to fail. That means it's not going to be generating power anymore. That means whichever power station is using this, and through the electric grid, suppose it supplies power to Delhi, and in Delhi you've got all these parliaments and everything else and marketplace and factories and so on outside Delhi, they are going to shut down. So because of my poor work, it's very possible that Delhi is going to collapse, or Delhi is going to have a power out for maybe 6 hours or 10 hours or God knows how long. That is the reason I have to do this job right. I have to make these measurements. These are to be looked at by an engineer. He is going to make sure in the evening, after he goes through all these charts, that things are acceptable. As far as business is concerned, things are acceptable to me. You know, I honestly was more than impressed. I could not believe that this man knew the value of his work. He knew it to the point he knew exactly the impact of his not doing the job right and its impact, you know, some hundreds of miles away on Delhi or perhaps some other place. He knew that very, very clearly. This is one example. Let me talk about the other example, a parachute factory. This parachute factory is also located in the north, and there of course we have a different kind of story to tell you. Again, like I visited BHEL, I went to this parachute factory, and this factory produced parachutes. And these parachutes were used by these amateurs, you know, the people whose hobby is to fly parachutes, jump off some cliff and float around and so on. These parachutes, they were fabricated in this parachute factory. And I walk up to a particular place and a workstation there again, because my talk was over and I had some time to float around. So I went down to the shop floor and I found they had what looked like a bunch of tailors. Tailors means they were, you know, cutting up sheets of plastic and sheets of silk and sheets of cloth, and they're stitching them here, stitching them there and so on. They're doing this. There was one gentleman, he was actually cutting the cloth. He had a template in front of him and he was cutting this cloth. First of all, I should tell you, in the North India, there are not many places where people use parachutes. It's all used either in the hills, which is really up north, or they are done in the south. Some places again where there are recreational facilities and people, you know, they take a jump either from an airplane or from a hill and they float around and they have some fun that way. Around the area where this factory was located, there were no parachute jumpers there. Now you walk up to this gentleman and he's got this huge sheet of cloth laid out in front of him, and he had this template also laid out in front of him, and the template was there like this, and you would spread the cloth on top of this, so the cloth would be spread, and then you take his scissor and you start cutting, and it cut, and you discard this part and you keep the cloth. This you would then fold up and you'd stack them up someplace. Then I asked him, what do you do now? He said, well, you know, I'm not concerned with that. I basically produce these triangles and I ship them over to the next department. They have a box and I go and pile them up in that box and then they do something with it. I said, sir, what is it that is actually happening here? What are you trying to do? And he said, well, in my language it is called chhatri. We are making chhatris. We are producing chhatris. Chhatris are kind of the colloquial word for a parachute. that's got a circular shape, and it's got canopy and so on and so forth, and there's strings, and of course the man who is jumping, he's hanging by the parachute, he's got some strings attached with his body to the parachute, to the cloth there. And this man's job was to prepare these triangular sheets, and these would be then stitched up, and the canopy would be prepared and so on. I asked him, sir, have you seen someone jump off an airplane? Have you actually seen the chhatri open up? Have you actually seen it yourself? And he said, no sir, I've never seen it. I said, what about maybe some other place? Have you actually, you know that chhatris are used by, he said, yeah sir, I know. They are used by people, and I've heard they are used by young people. They kind of, they have some fun and they do this. I said, what about you? Have you actually, so you are telling me you've never really seen a real parachute open up and the man floating down. You've never seen that yourself, right? He said, no sir. Just think of this person who is doing this, his sensitivity toward the user. He has no idea who the user is, or what he does, how he jumps, how the parachute opens up. I'm sure he was probably curious, but he had never had that opportunity to interface with a person like that. Well, this was not so bad. Let me tell you what happened after this. After this little visit to the shop floor, I had an occasion to have some tea with some people. These were the supervisors, and these were graduates. They were graduate engineers who were supervisors of these people. They were in charge of various shops. Somebody was in charge of the belt department, somebody was in charge of cutting department, somebody in charge of something else, and somebody in charge of stitching and so on. These guys, they were supervisors. They were at much higher level than these people there. They were having tea with me. We were sitting around the table, they were chatting about various things. Life in the factory, life in this, and so on and so forth. And the general manager was also there. He happened to be there. And I just wanted to ask the same question. I actually asked, gentlemen, you've been here a few years, 3, 4, 5 years. You're probably waiting for your promotion so you can go on to better jobs and bigger jobs. But tell me, have you actually seen someone jump off an airplane? Have you actually seen your parachutes utilized by somebody? And this is a city in the north, again in the plains. So again, there is no real local, no opportunity to watch these parachutes float around in the sky. There is no such opportunity there. None of these people had been exposed to that. They had been exposed to a site where they could really see a fellow jump off a cliff or a parachute with a parachute, and the parachute open up and slowly come down to the ground. They had not seen it themselves. They're young engineers. They are supervisors. There was one person who said, yes sir, I have seen a fellow jump off a parachute. I said, well, how is it? How is it that your experience is so different from these people? They also seem to be looking about the same and so on. They can't be much younger to you. How is it that you know about parachutes? He said, sir, I was really originally I was selected by the Air Force, but then for some reason I got hurt somewhere, so I was asked to go into civilian duty. So I've been assigned to this factory. I work here. This was the only person who had physically seen a parachute in use. Unless you have seen how the user is going to be using this object. Suppose I'm the producer of this object. If I've never been exposed to the person, I've never come face to face with the person who is the real user, do you really think I'll do a top job in producing this? So the contrasting pictures are this. The first one is the turbine, where the man knew fully well the consequence of his work, or the consequence of doing a poor job there. And the fellow who was cutting these pieces of cloth in a parachute factory, this fellow had no idea at all as far as the end user was concerned. So would he be sensitive? This is something that is very, very important. And this is what he's saying, making each worker responsible for the quality of his or her work. And that will not come by pounding on his head. It will not come by pounding on his head, by some philosophy. It will come only with a direct face-to-face contact. So you need things like the QFD and so on to come in direct contact with the user. Unless you do that, you just will never have that sensitivity. The ladies, when they serve you food, what do? They watch your face. What they have produced, how do you like it? Your face will tell them, without even saying, oh, food is outstanding, food is knockout, blah, blah, these things. they'll watch your face. Some gentleman who has preserved this special wine that he brought from France for you, he's got that bottle there and he pulls out that bottle and he lays it, he shows off, he says, look at this, chateau, some wine there. This I've kept, I was waiting for your visit and now that you're there. And when he pours it out and he gives it to you in a little goblet and he starts sipping, what does he do? He watches your face. And there he's coming in direct contact, face-to-face contact with the user. And he gets signals from it. He probably finds out, well, this Indian guy who's from the East, he loves fish, but he probably does not like my wine. And probably next time I should not be serving him this, I should be serving him something else. This is a sensitivity that you require. And this comes only when you've got face-to-face contact with it. So no matter what you do in terms of your logic, philosophy and everything else, you cannot forget the customers. You cannot expect to win if you forget the customers. That's very, very important. There are obviously some classical ways to solve problems, and you've got the definition of the problem, you collect data, you analyze things, and you generate potential solutions. You choose a solution, then you implement the solution and so on. But these are classical problem solving steps. This is somewhat different from what basically Deming ended up saying. Deming said, you plan what you're going to do, some corrective action you're going to take, you carry it out, you look at the effect, and then you act, which is like take the next step to come around. This is his PDCA cycle. This plan, do, study or check and act. PDSA or PDCA cycle. This was given by Edward Deming. He gave this. Process improvement obviously could proceed this way, and a lot of processes, they are basically worked at by this way. But in fact, there are more powerful methods. So refinements have been produced of this PDCA cycle. This is one example. And you can pause the tape, you can pause your screen, and you can take a look at these things, you can read them and see what they are. Not very different from what we saw in PDCA, except some refinements have been done. But Six Sigma provides you a much more powerful framework, and that framework is spelled DMAIC, DMAIC. This I am going to get into a little bit to give you a little glimpse of how Six Sigma is different. But before that, let me just remind you, Six Sigma does not throw away TQM. Six Sigma builds on TQM. So, we will catch a glimpse of some of the tools of TQM. If you have not used them, believe me, try to use them. Try to use some of these TQM tools and you will find how useful they are. Just this morning, there was an occasion, one student came to me and he told me, sir, teachers are late coming to the class. Just think of this problem. This kid is highly conscientious. He's really strongly motivated to learn. And he comes to the class and he finds the teacher is not there. He's trying to get into the building and he's finding that the class could not be started because of a variety of different things. And he said, sir, this is something I would like to analyze, I would like to understand. Then he and I, we went to an empty class and I drew a cause and effect diagram. I'm going to give you some examples of that. I will go there gradually. So, we'll call that process improvement. So, we are going to be looking at some process improvement tools. There are a number of tools available. As I get to that point, I'm going to pause for a minute. I'm going to bring up this issue of teachers coming late to the class. How did we tackle that? The basic TQM tools include flowcharts, check sheets, histograms, Pareto charts, scatter diagrams, control charts, cause and effect diagrams and run charts. They are probably listing more than 7 tools here because some of these are quite similar. What we have to remember is that each has a specific purpose. For example, the control chart is used to control a process, and the run chart is basically, the run chart is not probably marked here. The run chart is used basically to keep track how many, run chart is right at the bottom here, to keep track of how many items produced are out of specification. So, control charts have a different function. They try to help you control a process, to keep accuracy in control and to keep precision in control. 2 objectives. And what does the run chart do? It just tries to make sure your production is within specification. That's what the run chart will do. So there are different applications. So a process is there is input going on, and all these different factors, they might be impacting your process. So your sources of variation is something that we do not like. For example, we saw our friendly chart, which was like this one. And with the black distribution, you saw a lot of variation that people wouldn't like. And somehow we got it to the green distribution that has smaller variation. This is something customers would also like, because everything is fitting within the spec limits. How does this variation occur? It occurs because of all these different factors, they are not always in control. All these different factors, they are not always in control. That's why we end up with variation. So variation is something that nobody likes. Nobody likes variation. And in particular, quality assurance people or quality managers, they should literally go mad when they see variation. They should go mad and they should try to fix it. What are some of the tools? One way is to try to flowchart the process. Go from the beginning to the end, trace the process, and try to locate those spots where quality seems to be out of whack, out of control. Then you focus there, and you would try to take some steps just before that to try to make sure, again, the process comes within control. And there is this run chart, of course, and I have given you the results of it, and it can be used to identify when equipment or process, they are not behaving according to specifications. So this is really, it has got spec limits here, not control limits. It has got spec limits here. That's what it is trying to do. Then of course you've got this little data collection chart called the checklist. These are all TQM tools. Then you've got something called the histogram, which gives you a picture of the history of production. And if on top of this, suppose I'm able to superimpose specification limits, then I can find out, what are the parts that are out of specs, and which are the parts, what is the fraction of parts that is within specification. That's something that I could do quite easily with the histogram. When it comes to root cause analysis, the best tool for that is the cause and effect diagram. And the cause and effect diagram has the effect written on the right hand side, and the various causes, initially they are developed by doing speculation. You don't try to solve the problem directly with the cause and effect diagram. But first you try to speculate what are the different causes that might have caused this. And I'm going to go back that teacher coming late to the class problem in just a couple of minutes. Let's take a look at one finished cause and effect diagram. This is like one that is under construction, and this is the one that has been completed. So it's got many more details. Let me tell you now what happened in that class, teacher coming to the class situation. We went to this empty classroom, and we wrote down the effect to the right. We said teacher comes late to the class, and I drew this spine of the fish. Teacher late. And this could be caused by a variety of different things. And the student, of course, didn't want to be kind of put on the spot. He did not want to really come up with the factors himself. He knew many factors. But he didn't want, because I was a teacher, I'm a teacher, he didn't want to sound like offensive. So he held back a little bit. Then I had to provoke him a little bit. So I started out by saying, well, the teacher is late, maybe because the building is locked. Could this happen? He said, sir, yes. What about rain? Rain and flood? Could that also prevent this teacher to come? Rain and flood? He said, yes. Then we started saying, what about other factors? Is it possible that he woke up late? So he woke up late. Alarm didn't go off. And I acknowledged that. And we went on and on like this. And believe me, we found reasons that were really strange. For example, yes, indeed the building was locked. And the phone was not working, and so on. And would you believe the teacher did not know the time of the class? Because when we called up the teacher, he said, well, some students called, I didn't really know the right time of the class. And I said, till it is confirmed that the time is right, how could I start the class? Because maybe other people would be missing the class. So I didn't do the class, and so on. So this is like how you slowly do what we call root cause analysis. Then you start removing them. For example, if you found that the gatekeeper, the steward does not show up on time, the fellow who is supposed to open the gate open the doors, he does not show up on time. The class is supposed to start at 7:30 a.m. in IIT Kharagpur. This is our routine. And suppose the man with the key does not show up till after 8 perhaps, because that's his routine. But he does not quite know that once he opens the door, only then people can get in. So that had to be fixed. So this problem had to be fixed by in fact telling him what the time was for opening the thing. Rain and flood he could not probably do much about. But perhaps the access to the building could be controlled. If there's a huge puddle there, probably one could not walk through that, and so on and so forth. So basically this is how you do it. What about waking up? If this is something where the teacher has to change his habits, let it be known to him. But will you really start beating him up? Will you really start calling this teacher? Will you really start sending him emails? What you have to count on is how frequently, how often does this happen? If it happens like once a year or twice a year, that's okay. Everybody understands. But is this happening like 3 times in a week? Then of course something is wrong. Maybe he's going to bed too late. Maybe his PhD student is keeping him up in his office till maybe 1 o'clock or 2 o'clock, and then of course he's going to be late coming up. And this, I have personally experienced this thing sometimes. When students really stay with you for a very late hour, till very late hours. And of course you are then kind of wondering, what should I do? Should I ask him to go, or should I just complete this discussion? It becomes kind of a little dilemma. So in any case, the issue is this: if you have to find the root cause for an issue that is there, a quality problem that is there, you got to be able to construct this. Initially this is done on a speculative basis, as you see in this chart, that is the finished chart on the screen here. This is the finished chart. Then you start examining them. This is only one use of this control chart, of this fishbone diagram. The other use is if you've got definitive factors here, factors A, B, C, D and so on. And if these are control variables, if these are factors that you can control, you could take them high, you could set them at the middle, or you could push them down to a low setting. You will have to find out what is the right setting for this. And the technique for doing that, can you tell me what that technique is? I think some of you would remember. It is DOE, design of experiments. And design of experiments also is right at the core of Six Sigma. So it turns out that the cause and effect diagram is the beginning of a Six Sigma project. I have done it personally. Nobody gave me the factors. Nobody told me, Professor Bagchi, here are the factors, and just please play with those factors. I had to make sure that none of the important factors were left out of this list. For that, I had to get back to the cause and effect diagram. I really had to get down to this. I had to make sure all the important factors are captured. Then we would, construct a matrix and we'll start doing our experiment. So it's a very, very important tool. I just can't tell you how important some of these tools are, even in a large project like the Six Sigma project. Then of course you've got SPC, and SPC comes along not exactly at the start of your Six Sigma project, but in the control stage, DMAIC. So at that C point, when you want to stabilize the process, in order to keep it that way, use SPC to monitor the process. And what is the result for doing all this? If you start with the process, look at the distribution on the left hand side. It's wide. That means perhaps my product is probably out of specification occasionally. I should just remind you that here I've got control limits. I don't have spec limits, because what I'm plotting here is some variable like X bar or R, which are really statistical in nature. These are not individual measurements. Then of course, after some work, after some troubleshooting, I'm able to narrow down the variability. So variability is maximum at this end, it's medium here, and it's narrowest here. Hopefully more customers are going to be satisfied at this level. This is something I've got to remember. This is like one tool. How do I get ideas? Well, the best way to get ideas is by brainstorming. And there are those rules. If you have any doubt, pick up some books that discuss brainstorming and look through the chapter, or go on internet and just type brainstorming and just see what comes out. You'll get many people who are writing on this brainstorming. You'll find many articles on it, perhaps even white papers, and you just read them. It's not that difficult to basically learn about. It is somewhat difficult to control yourself when you're in a brainstorming session, because we tend to speak up and we tend to control others. Quality circles is the same way. Interviewing is like another way to generate ideas. Benchmark is a great way. And the Japanese method for 5 whats and 2 hows. That's like another method by which you could do that. Quality circle, I'm just going to be, basically displaying these screens here for you, these slides here. Quality circle is a team approach. Of course, it's made up of volunteers and so on. And it works very well, unfortunately, in the Eastern cultures. It does not work so well in the West because people tend to be more individualistic. That's why it does not seem to work there. Generating ideas, of course, brainstorming is a great way, and this is like something that you should really practice. And you should really see how a good person does that. Benchmark is a great way to find out how other people are doing the same thing, but they are doing it better. You just have to go there and observe what they are doing. So, for example, let's say you want to improve your study habits, or you want to come up with, with high grades in your class, as an example. Somehow find a person who is better than you and observe how he spends his whole day. Find out what all different activities does he involve himself in. Yes, his IQ may be different from yours, but what about all the other stuff that he does? Perhaps when he leaves the class, he goes to an isolated area and he glances through the notes. Perhaps he takes a pen and he marks all those things that he needs to get clarification on. Perhaps when he comes to the class, he sits right at the front bench and he's always interacting with the teacher to try to find out what is going on. Perhaps he tries all the problems that have been assigned to him. Perhaps he cross-checks the answers with other people. Perhaps he works in a group. So find out what all things he is doing and find out things that you are not doing. This is the way to benchmark yourself. His benchmark is here and you are here and you have to rise up to that level. This is also done by industry. Many industry institutions, organizations, they encourage benchmarking because they want to be competitive, not so much competing with each other because people may come from different areas. For example, here I've got American Express. They have a way to get customers to pay up quickly. And many companies have a real great difficulty in getting people to pay on time. Disney World, look at employee commitment. And every time I have visited the Disney World or the Disneyland, I've been amazed by the dedication people have there. These are the workers. They probably do not get a lot of money. Their pay is probably not very different from other places. But somehow the organization, it's been able to inspire them in a way. They feel they are there only to provide the service, to entertain people. That's what, and it shows on their face, it shows in their actions. Federal Express, for its speed, it is considered to be a benchmark. McDonald's for its consistency, whether it's Tokyo, whether it is Delhi, or it's New York, or any place. You go to McDonald's, you order something, you order a fish burger, it will have the same taste. The tartar sauce will have exactly the same, tangy feeling, and so on and so forth. It's so consistent, it's just amazing. You would not even know where it came from. Xerox for its benchmarking method. If you just want to learn about benchmarking, look at what Xerox does. That's like a great way to do that. So there are some details on benchmarking process, and I'm going to be flipping through them, and you can pause if you want, you can read through them, and you can find out exactly how this is done. So this is going to be basically a couple of slides are there to summarize what all things are there in terms of the tools and their utility. These are all TQM tools. They are all utilized in eventually going your Six Sigma projects. Your suppliers can also give you good ideas. That also comes along. Something you got to keep in mind is that in any of these things, whether you are drawing control charts, you are doing design of experiments, or any of these things, you are making some measurements. And you got to make sure your instruments are proper. And there are two very important things in regard to instruments. The first one, of course, is that the instruments have to be accurate. This is something very, very important. Instruments have to be accurate. So accuracy is something that's very important when you're using an instrument. And the second thing is that precision also has to be good. And let me define these terms for you very, very quickly. Accuracy basically says how close your average is to the target. So let's say my average is X bar. How close is it to the target, tau? The closer it is, the more accurate your system is. So if you're looking at an instrument, for example, if you're looking at these gauges which are on the screen here, you have to take a standard object and you know its true dimension. Then you take some readings with these instruments and you look at the average quantity. If that average turns out to be close to the target, which is the true value, your instrument is accurate. What about precision? What is that dimension? If I take multiple readings, x1, x2, x3, x4, are they kind of scattered around a wide space? Are they scattered here, 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 here? They're scattered over a wide area. If it is like this, then precision is lacking. But if the measurements, individual measurements of the same object, if they turn out to be close to each other, like this, I have precision, I have good precision. So it is the spread of repeated measurements that will indicate to you how precise that instrument is. And these are two things that are also very important in process control. When it comes to accuracy, we want to make sure our processes, they stay in control, they are accurate and also they are precise. To try to make sure that a process is accurate, we use the X-bar chart, the X-bar control chart. And to try to make sure my precision is there, I use what is called the range chart or the R chart. The R chart will make sure that you are able to get precision in the delivery, on the output side of the process, which I'll discuss again when I get to SPC. I'm going to be discussing these again. You just be aware of it. So instruments have to be right, and there are certain things that are called gauge R&R study. The fineness with which you can make measurements, your calibration should be right. Calibration, by the way, it helps you make an inaccurate instrument still provide you measurements that you can take to be corrected, calibrated readings. And if the instrument has been calibrated, you know that a certain reading is equal to a true reading of this value. That is done by the calibration plot. So this is something you got to keep in mind, and this is something kindly take into consideration whenever you are using an instrument. Please go through the records of the instrument and try to find out it has been calibrated using some standard methods. Then of course, if variation is there in the thing, then your precision could be impacted, and for that you have to do some studies, and you may have to run some special tests, special experiments to get an idea of how precise that instrument is or how poor that precision is. And this whole area is called gauge R&R. If you are collecting some data, part of that data could be because of the parts that you are using and part of it due to measurement errors. Part of that data, the variance that you see in the actual data, the numbers that you've collected that have come out of the instrument readings, those could be due to the true parts, and that those true variations could be because of the different parts you are using. These different parts, when they are produced at different times, there may be some natural variation. Their heights are different, their thickness is different and so on. That is the natural variation. There is a part-to-part variation. But if I am using an instrument to measure their height, then the instrument also itself can introduce some variation. So there are two parts of it. There is the parts variation, and then there is the measurement variation. It's very important for us to make sure measurement variations are as small as possible. And most of the variation that I see in the data is really due to parts variation, because that is what I'm after. I couldn't be bothered about the performance of the instrument. I really want to make sure the data that I see is reflecting the true part-to-part variation. That's what I'd like to see. For that, you have to do this gauge R&R study, and some special methods are there. I'll just mention this word to you, gauge R&R. So wherever you are, you please try to make sure people have done a gauge R&R study before you go into your TQM application, before you go into your control charts, before you go into your Six Sigma projects. Please make sure the gauge R&R studies have been done. Only then you start your Six Sigma project. This is like taking care of your groundkeeping, basically your housekeeping. So measurement errors, actually they themselves could be caused by people or they could be caused by instruments. If there are different technicians, we say if different technicians are producing different readings, the measurement system has a reproduction problem. And if the same instrument produces different readings in the hands of the same individual, then there is a repeatability problem. And these again have to be understood. And you got to make sure that this total measurement error again is quite low. And normally speaking, in industry people say measurement error should not be more than 10% of what you are trying to measure. That's just like a rule of thumb, that's all. It may not be good enough for you, but that is something that we'll have to do. Then of course is this issue of external benchmarking. That is like you take your workers to another company. For example, if there's one particular company that produces electronic parts, like inside mobile phones there are these little printed circuit boards on which they've got the transistors mounted and the resistors mounted and coils mounted and so on. Sometimes that soldering is not quite good and you have some defects in the instrument or the instrument stops. For example, even a little mouse here, inside there are some soldered parts, and if the soldering has not been done very well, you may have difficulty in using the instruments, for example. In the old days, the PCs used to be that way. Many of those, they came out hand assembled parts and they did not really behave very well. The issue was this: how do you produce properly soldered printed circuit board? A machine came along which is called a wave soldering machine. And this really lets the PCB, imagine the PCB floating on this, the little wave of molten solder, and the PCB floats on it. When it comes in contact with the molten solder, it picks up the solder, and the joints, they become properly tinned and so on, and the solder is perfect. Now this is all fine if my machine is controlled very well. This is a process machine and I'm basically floating these parts from one end to the other. And there's a heating stage, there's a warming stage and so on. Then I insert the parts and so on, and then I bring them over this thing, then I cool them off and so on. This is a process with different stages. If this process is not controlled well, you may not get proper outputs. There was one company where they were using this wave soldering system to produce their parts. And they had converted onto this wave soldering system because they got tired with their manual soldering. They had all these, the soldering guns, and it was hanging by a cord, and the worker would go there and you'd solder this, then you'd solder this, then solder this and so on. That's how he was doing his assembly. And they found this was highly labor intensive. So their intention was to produce good parts and also make sure they could cut back on labor requirements. So they installed this gigantic wave soldering machine. After 6 months of operation, they could not really produce good parts with this new system. They could not do it. In fact, they had to bring all those people that they had laid off back in the shop again, and their job was to take these parts that were not really behaving very well, and touch them up here and there and so on, touch them up so that they could be put into the real machines inside, maybe mobiles or whatever they were supposed to go inside. And they were really frustrated. And again, I got called in and I was told, could I help them in certain ways? And I looked at their system, I said, well, it looks like a lot of things really have not been aligned properly. So you have to do some study and do it. And the manager, like most managers, he was very impatient. He said, well, Professor, I don't have that much time. I've already spent 6 months and I think I've done all the training that I could, and still we do not get good parts. What do we do? What do you think we should do? Our professor obviously took some time. In 2-3 days, once I was brushing my teeth early in the morning, and I got this idea. Maybe what I could do is, I could load up these guys, these workers and a couple of supervisors in a mini bus, and I could take them to a place where they had a properly functioning wave soldering system. And I'd let these guys just watch. Don't ask any question, nothing at all, just watch. Watch this system in operation. They had their own system in their home base, which is their factory where they worked, and they would be taken to this new place, the other factory. They were just allowed to watch basically what was going on, because obviously the other company didn't want to share a lot of tricks with them, but they could really, like people come for sightseeing and so on, they could probably have these people come and take a look and so on. Later on, of course, I got them to talk to each other also, but that was because I knew people personally at both ends. I knew people, so I could bring those people together and I got them to have coffee together and so on, and that turned out to be a really successful project, a benchmarking project. But what happened was, when I brought this team of workers who were really bad performers, poor performers in the eyes of their management, and that were operating this poorly functioning wave soldering machine, I brought them to this other company where they had a properly functioning system there. these people watched the system for about half an hour. They were totally silent. And they watched it some more. After about 1 hour, they started watching a bit more carefully what exactly was going on in the shop. They found a lot of dials, a lot of controls, a lot of this, a lot of that. And these were not there in their own system. They were not there. They had like a temperature gauge, they had a speed indicator, they had something else and so on. All these things were there. They had a video camera somewhere. And otherwise the system was the same that they had back in their own home. They had the same system. But these people, they had many more other things that were almost like monitoring this thing. Particularly there were some gauges, speed gauge, temperature gauge and so on, they were there. And occasionally they found, that little, the wave was there, wave of molten solder. Some fellow went and took some samples out of it. He put a little, a little thing, and he dipped a little bit of it, and he took it out, and he did something with it. Then he came back, took another little thing. He was taking samples. Basically, he was trying to find out, was this getting oxidized? Was the tin getting oxidized, or was it still okay for some more run, another hour or run, and so on? These people, the visitors, they observed this very carefully. I actually asked them at that point in time, are you finding anything new here? And you've looked at the system and so on and so forth. Are you finding anything new there? I said, Professor, we can't tell you how grateful we are. I said, tell me, what did you see? I said, first of all, it seems like there is some relationship between speed and temperature and all these things. We don't know that. Our manager says, produce, so we run it as fast as we can. Now, I do not know, I personally do not know if any of you have, when you're young, if you tried your hand at the soldering gun. I don't know if you've done that. You have to give it a certain time to warm up. If you have to give it a certain time for the bead to become shiny, the bin of the tin or the lead to become shiny, you have to give it some time to hold it there till the junction actually takes place. Then of course you can let it cool. A lot of things have to happen correctly. So the master solder people, they really know this thing very well. And none of this actually had been optimized in the system that these guys had installed. They said, Professor, there are so many things we have to do. Can we just make a note of at what speed they are running and blah, blah, and those things? I said, I don't have that permission today. I'll try to get that. And perhaps you guys should go back and try to pull out the technical manual that you have dumped. You have a similar machine, so you must have a technical manual with it. So pull it out and just see what it says and compare that to your own running conditions. How did this happen? How did all this happen? It happened by benchmarking. It happened by benchmarking. This is like something that I will say, it just opens people's eyes. You don't have to do any training at all. They are smart. They can see. It's like you watching your buddy who is getting A after A in every exam, and you're not doing so. Maybe you're goofing off a little bit, too much. Maybe you're spending more time at the tea shop or something. Maybe you're staying up too late and you're too groggy in the class when you come in the morning. Maybe you're going like this in the class. You can't really concentrate. You can't really pick up much. If those things are happening, watch out. You're a prime candidate for benchmarking, and you can improve. If you keep your eyes open, if your ears open, and if you go there with an open mind, I'm there to learn, I'm there to see and observe and make some notes. You'll end up picking up a lot of tricks, and these are shortcuts. You don't have to try this and try that and then get to the right spot. You'll not have to wake up at 5 a.m., start your studies, 6 a.m., start your studies, 7 a.m., start your studies, and see at which hour, if I wake up, I get maximum marks in my quiz. Maybe it is 6.5 or something. You don't have to do that. Just watch that other fellow. He's similar to you. In most respects, he's similar to you. The Japanese obviously have other methods, like the Shingo method. And then there's the poke-yoke method, which is like, you see a lot of these things when you look at electrical points, for example. I'll try to see if I could find there's a plug point there on the wall. You can't probably see it because it's outside the range of the camera. But many times, if you look at the sockets and if you look at the holes in the plug, they have used some bit of poke-yoke so that a 5 amp plug will not go into a 15 amp plug, 15 amp socket. It just won't, because they've applied some bit of poke-yoke because people made those mistakes. I remember in the early days when the connections were difficult to find, the telephone wallahs, the guys who fix telephones in your homes, they use the same plug to, basically take a two-prong plug, and that is used by, electric lamp type of people. And they use the same plug for telephones also. So I have physically seen a lady, quickly pick up a telephone and plug it into a wall plug, which has electricity, and set a little fire there. Luckily, she was safe. But this I've seen with my own eyes because the plugs looked exactly the same. There's no difference. That is not poka-yoke. Poka-yoke is when the plug shapes are different and plug sizes are different and so on. This is like something by which the Japanese produce a lot of good quality products. So there are, in the end, when you look at service quality, the moment of truth is when you directly come in contact with the customer, face to face. A lot of things happen then. There is a lot of interaction, and at some point in time people say, you get the message. Why is it that we call something service driven? Because we look at tangible things that the customer is looking for, we look at convenience, we look at reliability. If he comes back again, does he see the same thing? Responsiveness, time and so on. This is like one whole area, and there are slides here that are about service quality. And service quality has obviously a lot of these things. If it's like a hotel, for example, you'll see facilities that are clean. Convenience is something that you'd like to see. A lot of convenience is shown there. Reliability is also again something that you'd like to see. Responsiveness, and you can read them, you can really see, and you'll probably agree with them that these are all vital when it comes to providing service. I should tell you about one or two of these things. For example, a surprise that I got when I went to a French hotel. This was near Montreal. I walk in there, and as I was getting off the taxi, there's this bellboy. He walked up, and he said, "Bonjour, bonjour." I said, "Bonjour." Nice, good, wonderful, and so on. And he just asked me a very simple question. "Sir, have you been here before?" And I said, "Yes, I've been here before. I've stayed here before." But it was quite some time back, about a couple of years back I was here. That's all. Then I walk up to the counter, and the young lady is there, and she looks at me, she gives a wonderful smile, and she also says, "Oh, it's wonderful to see you, sir. You're back again, it's wonderful." I was really surprised, I was shocked. I'd never met this lady. I could never remember that I'd met this lady. How was she saying this? You know what happened? The bellboy, because he asked me that question, "Sir, have you been here before?" He was standing behind me. He was with my bag, and his hand went like this. I, of course, couldn't see that he was doing that behind me. And the lady picked up the signal from there. "This is an old customer, and you're especially courteous to me." And I felt like I was wanted here. And I stayed there one extra night. So they got some more business out of me, because I felt this is the difference of quality service. This is approaching Six Sigma. I'll continue with the theme as we move into this. I'll continue with the theme. Thank you very much.